Hello and welcome to day 12 of Advent of Code 2022. Hill climbing algorithm. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. You asked the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on, up to the highest elevation of Z. Also included on the height map are marks for your current position S and the location that you get the best signal E. Your current position S has elevation A, and the location that should get the best signal E has elevation Z. You'd like to reach E, but to save energy you should do it in a few steps as possible. During each step you can move exactly one square up, down, left or right. To avoid needing to get out your climbing gear, the elevation of destination squares can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to elevation N, but not to elevation O. This also means that the elevation of the destination square can be much lower than the elevation of your current square. For example, get S and E here. S is our starting point. Elevation A and E has the elevation Z. Here you start at the top left corner. Your goal is near the middle. You could start by moving down or right, but eventually you'll need to head towards the E at the bottom. From there you can spiral around the goal. B, C, and so on. In the above diagram, the symbols indicate whether the path exists, each square moving up, down, left or right. The location that should get the best signal is still E, and dot marks unvisited squares. This path reaches the goal in 31 steps, the fewest possible. What is the fewest step required to move from your current position to the location that should get the best signal? Suppose we have the E here. Yeah, and we'll kind of see a big mountain here before we have some A's, some C's and stuff like that. Yeah. Okay. Then let's get this into our example input. We have an example solution which is 31. And we have our input, which is this one here. So not absolutely sure if we really need it here, but let's just implement our standard vector data class vector 2D, where we store an x value x as an integer, value y as an integer. Then we just create our we already have to define somewhere, so let's put it for now into here. Then I would say we can create some constants of this. We'll call them var left is equal to vector 2d, and actually this one, and we'll initialize the vector left is -1 and 0. With left, right, no. Up, right, down, 0 and 1 and 1 and yeah, actually we usually orient ourselves on what we parse here, so up would be -1 and down would be 1. So and then we would have data, make it a class. We would we can relatively easy access the neighbor. So we call it cell. We put in a position, which is a vector, and we put in we'll also create a list of neighbors here. Which we do we want to have an extra map? A position, and then we put in the character. Height. Height, which is a char. And just operator, I think it's called plus b vector 2d, which returns a vector 2d, and it's operator fun, which then just returns vector 2d x plus b dot x and y plus b dot y. Get this. And we also want to keep track of our positions that game. So this will never change the cell, but maybe also want to have something. Do we want to have something like a game state? No. And the game state that will represent us. So this will be our position. Vector 2D. We would also have a set of it's either cell or is it vector? I think it should be vector, which we would call visited. I think we might need that as well. And we would also like to have our path, which is gonna be a list. Unsure if we need this cell thing here for now. So then let's start parsing. We've already learned that E is at elevation Z. Yes. So we start by iterating over. Let's already create a map. Val map is equal to mutable map of. We want to have the vector 2D, and we also want to have the cell, and which is the line index. Should we can actually try it, lines dot in for each indexed. Then we have the X position here. Is it though? No, it's the Y position. And we have the line here. Yeah, okay. Index, and this is the line. Then we say, and then for each of those, we want to take our line, and for each indexed, do the same. The only thing we call this here Y, and this one is X, and we call this one, yeah, C is fine, but let's call this one L. And for that, we would like to create our vector. Current position is the vector 2D of X and Y. And then we want to take our map at position, current position, and we want to insert, kind of want to insert a jar, but we want to have some, we need some special treatment here. If C is equal to S, then we will say have here the val level C, which would then be an A. Else, if the C is equal to the E for, I guess, emitter, then we would have the level set. Else we would have C, and we want to assign level C here. But we also need to keep track of start. Start will be vector 2D. Why? Vector 2D, and oh well, it will be of type vector2d, but it will be null for now. Then we'll set, if we're here, then we set start to current position. If we are at the else, we set emitter to the current position. And if we're here, we do check not null, start, emitter, and we here would need to create this cell where we put in again our current position, the level as a character, and we check those inputs, and we need to return something here. Okay, so far so good. We'll now can figure out the neighbors, and we can actually we have those vectors here. And we can now actually already define the neighbors we can access, and we can do that by iterating over our map. Now already set that, so would create a neighbor map for now. Navigate able map, which is a mutable map of, still call it vector2d, and of the cell here, and I would have a neighbors, and this includes a cell, and it also includes the neighbors as neighbors, and we'll insert them here as a map of vector2d and cell. The vector2d will be the direction here. Direction to neighbor. Then we have our navigatable map where we have two cell of neighbors. That's fine. So we take our map for each. And then we will we'll check map dot we could actually do something like all directions here, which is then all is equal to list of left, up, right, down. And then we would say vector to the dot all dot all dot map it map not null filter this is underscore current cell where its dot height is smaller equal current cell dot height plus 1. So this would then give me all the directions. And then I would say we want the cell with neighbors where we can put in the current cell and the directions. Because this will take all the vectors, map them to not null, map them to the cell value, and we want to have in there map to not null. Yeah. Well, it's would actually be an associate with then we would filter its dot value is can I say something like well, then I would just say filter key underscore cell. Can I do that? Okay, then I think I need to do it dot value the was? What's going on here? Mm-hmm. Mm-hmm. Not 100. Mm-hmm. We can actually also do it like, no, we can't because we want to filter it here. And we can't map it right. No, I think we can. Map to not. Map not null. So n for the neighbor, it would be this one. However, if n is equal to null, or n dot height is large, is exceeding our current height plus 1, then we will map this to null, and else we will map this to a direction, and to the direction which would be it to n. And directions would now be a list of pair of a vector and a cell, and we can now just say to map, and then we would have our directions map here. And this is just an associate keys dot associate with, and it would no map values. Would that work? Don't really care. Navigatable map. At position, current cell position is equal to this. So we can still keep those up there. We could have kind of special treatment because our emitter, well, we can also check that later, so would be fine. And yeah, I think we can now start. Let's just check where the S is here. Okay. And yeah, Then we can take our, then we need to do our path, which we have the game state, which we can copy that, but yeah, let's try to do a fast solution for or an inefficient solution for traversing the path first. So well, but we already need the best result here. Could already do an kind of search. We don't know. We know the operations. Could we do something like walking back from here? We could set the minimal cost of each of the surrounding cells with each of their neighbors minimum to get to the emitter. And by doing so, we'll just do passes, and at some point we will hit the start. And we would, with every, do we know we can reach it? Yes, we can. Or we wouldn't count. No way we can actually get the neighbor. We could actually spread from here down to there, and at some point we'll just set all of the fields. And this then should give us an optimal solution. So we can do the following. We can have our do we want to swap those lists? I think we can. Mm-hmm. Yeah, I would actually start by. I want to solve this by sending the signal, so to say, from E and just traversing where it could go. So I would say we have the current step, and in there we have a set of, this will be a val, a set of, and it's only gonna be the emitter. And we have, yeah, the current set, and we will at most need the, well, and we'll just do while just take the current steps. I just think we need to take out the first of those current steps then. So we take our emitter, we'll all up, left, right. Our emitter's position. Our emitter is a check not null. This doesn't make, because it's set there, so it can't infer the nullability, so this doesn't really get us the value there, but we can just we'll call it emitter F start, emitter P, and we will just say val start is equal to start P, and emitter is emitter P. So we can get rid of this, and we don't need to have the checks. And we'll now take our emitter position. Yeah, this is already the position. And we take then we loop over all our directions. D in vector to D dot all, and we say emitter plus D, then we can get out our navigatable map. And do a lookup of this one. And this is current. And then we would also keep track here of, with a map minimal distance is equal to mutable map of vector to and an integer. So then if we'll have a current distance bar current dist, which is equal to 0, or yeah, well, let's start with 1. If the current is unequal to null, then we have a neighbor, then this thing exists, and then we want to check if the current direction to neighbor keys contains our position, which is it's the limiter, it should be, well, this is the current neighbor here. Current neighbor. And then we say with neighbor, it's just a current neighbor. So, and then we check if the current neighbors, they contain our position. If that is the case, we'll just take this one, current neighbor the cell dot and set it to the current distance. So set this one to the current distance. Yeah, but I could actually go back as well. So even if it isn't in there, the thing is I have actually two neighbors. I would have all the I'm just thinking what is the most useful solution we could do here. If we go from set and spread the signal, yeah, I think we'll do it a little bit. We can keep the minimum distance. This is fine. The current distance. Would it affect us? If we take the neighbors of this cell, this doesn't really work. Because we would also need to get the reverse neighbors. So it's actually a really easy graph traversal, but I haven't done it for a long time, which is a bit annoying. So there is a priority queue, but how does it? Queue of cell, but how can I? Now I can do it greedy, I think, as well. At least I think I have an idea how to solve it. So then we will have our priority queue, which will say wow, cells to visit. We can keep track of this with actually having our path in there, which we could then use for do we need the visited set for path for the game state? I'm a bit unsure. We can give it a try. we can implement the comparable of, I think you need to specify the same case here, right? And we would just, it's I think always a minus b, so we would just say path.size minus other.path.size. Oh yeah, return. And then we would put those game states in our priority queue here. And we would say states dot add game state would be start. The path for now is an empty list, and we would have this. In this case, if we copy it, it also can be immutable, same as here, the same as here. So, and then we can have an empty set, and then we would iterate over our queue. No, we want to remove it then as well, while true for now. Then we would say states dot first, or how is it, pop, or deq pop. Oh well, let's go first. Val first. Is there priority deq as well? Yeah, well, and then can we say states dot remove? Yes, we can. First. So, and for all our first, we have the navigatable map, where we can just get the first position, and we have the direction to neighbors. This can be a get values. And for n in those, we can actually add them to our states with a new game state where take n is n would be we can have the key and we can have the neighbor here. Do we need to pack it? I think yes. Then we can take n the position. The path will be states plus the path. Do we want to keep the directions, or do we want to keep the, I think we can just keep the states is states, it's first dot path plus first dot path, no value passed per meter visited. Yeah, okay. And visited, not really sure if we need that though. Yeah, for now I don't think so. Can we just do that? Yes, we can. We don't need this here then. And then we can actually add the states, and we can have a well, we have the priority here. We have the path. Do we know at which cost we have it? Keep track of all states, and then we'll try to get the cheapest one. So yeah, then we have the condition that if first what is it, position would be equal to our start, then we've actually solved the problem. Then we can actually set our var costs. Yes, let's say -1, and we say then just costs is equal to first dot path dot size and costs to string. And we can break the loop here. Not 100% sure if this will work, but let's give it a try. So, and will come. Still 2 minutes left, let's hope. Doesn't like that. Yeah, okay, this is start P now. Same for the emitter. Expected is 31. We've solved it with 0, which is interesting because it means we set the cost somewhere. But we'll actually need to check this with the emitter. So, but at least this cost is correct. Yeah, and this doesn't really look good. Unfortunately. We can have a look into it. So our states queue has exactly one element, which is 0, 0. Yes, the start is 0, 0 and the path is empty. Then we've not reached the yeah. So, and let's just check how does our navigatable map look like for 0, 0. We should have 2 values in here, which is we move direction right and we move the first is a game state, right? Yes, no, that could actually work. Navigatable map. And we can say we can move to the direction right and we can move to the direction down. Our path will include the down here. And the path, and we would now go into here. We would now have the states path is size 0 and we are already there, right? Let's just do some runs. I think what will maybe need to check is that we don't need to go into the same state another time. I think we'll are here in a loop and we'll need to prevent that. Yeah, we'll try to sort it out, and we'll get back. Or we'll not get back with the stream, but we'll post a solution video on YouTube if I'm done with that. Thanks for joining. Have a nice day.